So I just wanted to start just with some background. So the motivation for this really starts from systems that we build to cool the ship with water spray. So we did a number of those experiments, and in that history, we started with a white painted ship and realized that it didn't really heat up, didn't show the benefits, so we tried to paint it dark gray. After sending the samples, we realized that this paint was actually LSA pigmented. And then we approached SOC to see if we could follow this up with wetted surface property measurements. So they took a stab at that back in 2023. And last year, we tried to do a more formal representation of this, and we actually went searching for this original gray. The one we ended up with was non-LSA. And so we wanted to figure this one out, do more, run those experiments again, and attempt to fit that data. So, as I said, the first thing we want to answer is, why did we not reproduce that paint? So we went and got some other samples, so we're going to compare all three types. Moses is going to take you through the repeat of those measurements. And then I'm going to present a new model because the Sanford-Robertson that we tried to do last year didn't really work. And then I'm going to take that through a set of different tests to show you what the impact of this new model is versus what exists.
Thank you. At Surface Optics, we make reflectometers, and I was sitting here kind of smiling, seeing all the hyperspectral imaging, but it's, a sister technology. And we're able to, with our systems, collect continuously reflectance from 250 nanometers, really out to hundreds of nanometers, but our specialty is out to about 25 microns. Sorry, I think I said hundreds of microns we can get out to. And that allows us to collect full reflectance. We're able to differentiate between specular and diffuse. We're able to do different angles, complete reflectance. And then we also have bidirectional reflectance, which is kind of a niche type of reflectance where it gives us control over all four angles, the position of the source and the position of the detector. So one of the big differences I'm noticing between what a lot of the other work is presenting in ours is in a laboratory setting where we're controlling a lot more of the variables, and yours is out in the field. And that's going to, it has different challenges. We're not quite in a real world setting, but we're able to control other variables to simulate different things. And so I'm just going to talk about the measurements that we collected, and then we're going to put them into the ShipIR model, and that's gave some really interesting results. We had a customer who asked us to cool some samples, and we started getting water condensation onto the sample because you cool things and it's cold and warm air comes and water condenses, and that was messing up our measurements. And then we realized it was an opportunity to measure wet samples. And what we were able to find, we used just a thermoelectric cooler in our SOC 100 and the 210. And we found that we were actually able to take measurements of the sample and maintain its wetness through the measurement. We weren't sure. You blast it with a hot source, it might evaporate water. And we're able even to control the levels of wetness. So as you can see on the right-hand chart, there is a dry paint, wet, and even more wet. Controlling it, predicting it, that's a different subject. We couldn't quite get there, but we're able to have it wet and have different levels of wet. And with that, we were able to start to see some pretty big differentiation, particularly in the infrared. So if you look as you get towards the visible, the dry and the wet paint in terms of reflectance look exactly the same. But as you go into infrared, they start to deviate, and you can use that to distinguish between a wet paint, which for a naval paint would be a typical use case. Same thing here, just with infrared, with the specular diffuse partitioning, you can see that the dry paint and the wet paint have a different ratio of specular and diffuse paint. So this is just some of the things that we're able to do. we took the three different paints, the 665, 979, and 990, and we performed a measurement on each of them from 250 nanometers to the 25 microns. And actually, what's kind of interesting is that they basically all look the same. And on the outset, our motivation was to find the paint with the low solar absorbance additive. And we discovered that that's actually quite hard to acquire. And for some reason, the way that the paint was made 20 years ago is not the way it's made now. And as we go through these different features, we'll start to see through the simulation, through the modeling that David did, that this allows him to create his hybrid model. BRDF, in this case, we just did one slice. That means the source is sitting behind the sample. The sample comes and the detector moves in one line in the same plane as the source. This is where the only difference that we really see between the three paints, the original paint that we measured, the 665, the wet sample had a much lower reflectance, and in the 979 and 990, the wet sample does have a lower reflectance as shown here, but I'm pretty suspicious of these results, and I'd like to retake them and make sure, see if there's some way that we can verify that the paint is staying wet throughout the duration of the experiment and seeing the same level of wetness. We're trying to reach some equilibrium, but once a source hits it, temperatures change, and so there's still some variables that we need to lock down. So our conclusion is that we do know that it's maintaining some level of wetness during the HDR measurements, which was going to be our biggest technical challenge. And we do know it's happening with the BRDF. We need to try and tighten that up to see if we can maintain the same level of wetness throughout the measurement. We also think that there's some temperature instability, so there's some drifting from that that we'd like to see if we can control. We've also considered maybe adding some salinity to simulate an ocean a little bit more and see what happens with that. And some quality control. So with that, I'm going to pass back to David, since he will talk about the modeling.
Thank you, Moses. So yes, as I said, we have this mystery of the LSA paint from 2008. So we still have the original SOC measurements that were done, and here I'm showing that stacked up against these three samples, and so you can clearly see that older paint had this incredible reflectivity that we can't reproduce with the paints available from that same vendor. So it remains a mystery. I'm still in discussion with them to figure out what happened in the intermediate years. So the other part of this is just having this model objective. So I talked about what we did last year. We were trying to fit the existing material file that we have to his wet measurements. Wasn't very successful. So I took a different approach this year, and that's why we're calling it 2.0. What I'm going to show you here is a new multi-layer approach. So we're actually going to apply a water film on top of the substrate, which is the dry measurement. And we're going to compare that against what we've been typically assuming now, which is to just cover it with a water film model, which is a specular reflector. We didn't worry about the transparency of the water. We were primarily concerned about the mid-wave and long wave, but we've run into this problem where some cameras are so wide that they pick up the near reflectivity, and that model doesn't work so well. So to show that, I'm going to show you a couple of vignettes. One is a flat black, just to show you the behavior in the diffuse. And then we're going to look at two examples here. One similar to the diffuse, but with the LSA paint, the old one. And then also one with this, one of the examples we measured recently. So I'll try to be brief on the modeling. So you know that water is a specular reflector, and it's well understood. You can get the index of refraction and extinction coefficient across all wavelengths. So that was already in our C model. The difference between this and the C model is that the C model is semi-infinite. There is no, like, whatever goes into the C disappears, doesn't come back. But in this case, the film is so thin that we have to worry about what happens when it goes in and back out the film. So we need Snell's law, we need some conservation principles. And so I just wanted to document, so we have a water film property that has a specular reflectivity, it has a specular transmission, And then the substrate could be one of anything. So there's some absorptivity there. If it's a window, it could be a specular transmitter. If there's it's definitely going to have a specular component reflectivity, as the HDR data shows us. And with the partitioning, we can also have this diffuse component. So we then work out what is the net effect of that on the film. So we have these equivalent specular reflectivity, transmissivity, diffuse reflectivity, and then absorptivity, emissivity. The first two are fairly straightforward. They're just the effect of the water. The middle one there, the third one, is probably the most difficult. And I've kind of tried to quantify it as this diffuse transmissivity, because what happens is it goes in specular, but then it hits a diffuse surface and it rebounds in all directions. So how do you quantify that theoretically? So it's really just a hemispherical integral. And when it comes right down to it, what you have to do is you have to integrate that back out transmission through the water film over all angles. And that's really what it amounts to. So that's what's been added to the model. And the first example I want to show you is just two examples. One is the hull film cooled example. So that's the full up model with the thickness. And I'm going to compare that against the same panel, but just painted with temperature, which will invoke the existing model, because it can't, this new model doesn't work if I don't have a thickness applied. So this is just a temperature vignette, so I've actually matched them. I've run the hull cooling model to steady state and then obtained the film temperature of that and applied it to the other model. So the match in temperature, this is showing you that it is a deterministic model. And what happens is we spray water with a flow rate, and then that water basically cools off the panel. And the other thing that happens here is all the sun goes through the water film, heats up the paint. So whatever solar absorptivity the paint has, it's going to take on that heat, and then the film is going to remove it. And you can see that showed up in the heat transfer between the plate, the panel, and that water film. Most of the energy is actually being evacuated by that film. So when we take that model and then we go and look at it, and what I've done is I've expanded out of the traditional band. I've looked at the near infrared. You can see that the left-hand side, which is that existing model, it grossly overpredicts the radiance. The one on the right is the actual film cooled panel with the new model. And you can see that because this is a black body and the water is transparent, there's very little emission in that band. But as we go through the thermal wavelengths, the mid-wave, we're getting a little bit more reflection off the new model. And then in the long wave, we're getting a little less. But if you look at the numbers, you can see it. So the band one, the near infrared, huge overprediction. Mid-wave's a little bit underpredicted, and then the long wave is probably accurate enough. The second example is I wanted to show you the vignette where we compare the two paints, the older LSA paint and the non-LSA paint. And I kind of skipped over this in the first shot, but both of these cases I've just shown you is having the sun illuminating the panels and the observer in line with the sun behind him. And here we get different temperatures because both are using the film cooling model. Okay, so the LSA paint is lower in temperature, but when we go into the near infrared, it's actually emitting much higher because we've got that LSA property. It has a higher reflectivity. That transparent water model is sitting on top of the substrate, and we get a really large reflectivity. But when we go into the infrared, the thermal infrared, both the mid-wave and the long wave, we end up with numbers that are much closer. And again, if you look at the numbers, they're within 2%. So, but in the near infrared, huge difference here between the two because of their difference in reflectivity. Now, just to make things even more interesting, I introduced a corner target. I kind of borrowed this from radar, but there's actually three corners or three panels oriented 90 degrees to each other, set up the same problem. Now, what I've done is I put the sun kind of in the middle of the cube, so I get a maximum amount of heating inside there. And in this example, I'm showing you the dry corner versus the hull-cooled corner. So you can see the dramatic decrease in the in the thermal signature of that. You can also see the multi-bounce effect of the corner, especially when you have an LSA paint. So you get multi-bounce solar reflections happening and it affects the temperature there. And it's a much more complicated case, so we had more sample points. Don't have time today to go through those, but I just wanted to show you taking that example and then showing you the corner with the temperature set, like the old existing model, versus this new hybrid model. Similar solution, I've insulated the backplate, so this is not two-sided anymore, so the thermal problem is a little bit simpler, but we have multi-bounce, and you can see here the Sol IJ is the collection of multi-bounce on one example here, and you can see that it's almost equal to the scattered sunlight from the background. So it's really important to include that when you're looking at LSA properties. So again, I've temperature matched them. We go into the near band, and now we're getting a lot more multi-bounce reflectivity on that existing model, which isn't there if we include the transparency and the film effectiveness of this hybrid approach. But again, as we go into the thermal region, we get very similar properties. And those numbers are vetted out as well in the differences. So not as bad as that black body example, but still important, about a 40% over prediction. And what that really tells us is that when we had that simplistic SR version of the water film, it was okay if we were sticking in the thermal region. But if we expand the analysis to include near infrared, then we really need this more advanced hybrid approach. And the next step is to expand this hybrid model into the material input API that we use to take SOC data and input our material files. What we want to do is we want to do direct comparisons, because I didn't show you HDR data, I just showed you panel radiance data. We also have the plan to add a similar NK model for the paints. Why do we want to do that? We want to do that because the Sanford-Robertson model really doesn't handle raw metal. Raw metals have a depression that Sanford-Robertson really doesn't take into account with incidence. And then the other thing we want to do is we want to expand this hybrid model into the thermal solution that we have. Right now it's very distinct. There's like a solar band and a thermal band partitioning that goes on in a thermal solver, and we want to incorporate some of the improvements that came in with this hybrid model. So that's it.